So we're going to try an experiment today. We'll see how this actually, how this works and whether I'm coordinated enough to write on this and talk to you at the same time. If it fails, I'll go back to a regular remote control on Friday. So we're going to finish up the periodic March chapter for the P block elements, the main group elements. And then today we will actually start to move on to transition metals and coordination complexes. Unfortunately, the first chapter there is not the most exciting because we first have to learn how to talk to each other when we're discussing coordination complexes, which means, of course, everybody's favorite. We have to go over how to name compounds. But it's not so bad. Not as bad as trying to name spinach when you're an organic chemist. But anyways, before we get there, we have to finish up the main group elements, and we left off with the heavy chalcogens. Say that 3 times fast. So sulfur, of course, is right below oxygen. It's a yellow powder. It turns out that sulfur is one of those elements that has many, many different elemental allotropes. Okay, so you can have S2, S3, S6, S7. You probably were already introduced to S8 because it's one of everybody's favorite symmetry questions. And so on and so forth up to S20. S8 is by far the most common elemental form of silicon. Of course, sulfur. Wow, we're going to have one of those days where I can't keep track of what I'm saying. So obviously, because we're dropping down from a 2p element of oxygen to a 3p element of sulfur, sulfur is considered to be soft compared to oxygen. It's a very, very good donor atom towards transition metals. So we'll see a lot of sulfur-type ligands for transition metals. And then the other thing that sulfur by itself does really well is form bridging species. Okay, and so a lot of times you'll have 2 transition metals with a single bridging sulfur. We would call that a mu2 sulfide. You can have mu3 sulfides. So this actually looks like the sulfur is capping a trigonal face that's presented by 3 different transition metals. And you can also have a mu4 sulfide. So now this is kind of weird, right, because it looks like sulfur is making too many bonds, right? We know oxygen can only make really 2 bonds. Sulfur in this case can make 4 bonds to different transition metals. And we'll talk exactly about how that happens. But in a way, it's kind of satisfying because you can obviously see that the sulfur can adopt basically sp3 hybridization. Right? Okay, so when you're talking about sulfur compounds, you have to talk about the halogen complexes of sulfur. And again, we don't really think about this very often, right? Because we typically think of P block elements bonding to metals or something like that, not to other P block elements. But it turns out you can make S2F2, probably not a surprise. In that case, the oxidation state of both sulfurs are +1, because I'll remind you with oxidation state, we assign both electrons in the bond to the more electronegative atom. So in the case of something like the S2F2 complex, the electrons in the sulfur-fluorine bond go to the fluoride because it's more electronegative. The electrons in the sulfur-sulfur bond get split evenly when you're assigning the oxidation state. This again differs from formal charge. If we were assigning formal charges, every single bond would get split evenly. Another interesting one, S2F2, you can see I've written it out as SSF2 to indicate that the sulfurs are different. Obviously, one sulfur has 2 fluorines bonded to it. The other has the sulfur-sulfur double bond. So in a weird kind of way, I look at that and I think it kind of looks like a ketone in a weird way. I'll admit it's not a perfect comparison, but you get what I mean. You can have SF2, again, probably not surprising, kind of looks like water. We can get more complicated. That one looks really weird. So we have a sulfur-sulfur bond. One of the sulfurs is bonded to a single fluorine. The other sulfur is bonded to 3 fluorines. SF4, S2F10. Okay, so we can add lots of fluorine to sulfur. And I think one of the things that this drives home is that fluorine, which we'll talk about in a minute or two, is a very, very, very oxidizing element, right? Again, if we're assigning oxidation states, the sulfur in that SF6 molecule is in the +6 oxidation state. If we think about where sulfur is on the periodic table, we always talk about those elements being the most electronegative there are, right? Fluorine's first, oxygen is second, chlorine's third, and then it kind of starts to spread out. But largely we think of sulfur as being a relatively electronegative element, yet we're still taking it all the way up to the +6 oxidation state with fluorine. Now again, the ability of fluorine to act as an oxidizing agent is highlighted by the fact that if you use a different halogen, you're not going to reach those fantastically high oxidation states for sulfur. So S8 will react with chlorine to make the analog to this compound in the top left, S2Cl2. And if you have excess chlorine and an iron Lewis acid catalyst, you can get to the chlorine analog of SF2, but that's it. You don't make any of these other oddball structures or ultra-high oxidation states of sulfur. And of course, the same is true for bromine or iodine. They don't have the oxidizing power to generate, for instance, Si6. Just doesn't happen. So speaking of the halogens are a case where the octet rule works pretty darn well. Okay? Halogens like to complete their octet. Basically, all they need to do is take up one electron. So for all of the elements, the only allotrope is the X2, so fluorine gas, chlorine gas, bromine liquid, iodine solid. HF, bad news. You don't want to get exposed to HF. It will leach calcium from your bones. Fluoride is so calciumophilic, it will literally take the calcium from your bones. Worse, it'll take calcium from your ion channels and kind of like, well, it's over, right? Calcium is used in communication. So it's really kind of neat. Well, no, it's not. If you get a drop of HF on you, it will literally burn right through your skin, right through your flesh, right till you get to the bone. You have to treat it with basically a toothpaste type material that has a bunch of calcium in it that tries to bind up the fluoride before it finds fluoride from your body. Pretty darn, let's see, okay, this is being problematic. Okay. So anyways, bottom line, try not to get exposed to HF. Okay, so fluorine, we just mentioned, incredibly powerful oxidizing agent. It's the one element that will allow many other elements on the periodic table to reach their terminal oxidation state, like we just saw for sulfur. It was discovered a long time ago from the electrolysis of HF. So we talked about electrolysis experiments. You take an HF solution, you basically pass a current through it, hydrogen bubbles off of one electrode and fluorine gas bubbles off the other. But the first chemical synthesis, i.e. non-electrochemical synthesis, that's not a typo. 1986. Of course, were you guys born in 86? Oh, jeez. I have bad news. You just all lost 20% on your grade in the class. I was in high school in 1986, thanks. That wasn't funny. So 1986 seems like just yesterday to me. You don't remember it, but that's the first time fluorine gas was synthesized in the lab. To me, that just seems crazy, right? This is an element gas that we had to wait until 1986 to make. And you can see that it was made in a pretty unusual way. So you can start with this dipotassium manganese hexafluoride, and you react it with antimony pentafluoride. We've already seen the antimony pentafluoride. Does anybody remember where? Superacids, exactly. SBF5 is an incredibly strong Lewis acid, and it really, really wants another fluoride anion. So what happens here is this two equivalents of SBF5 come in and take two fluorides from the manganese and make this metastable manganese tetrafluoride, which then reacts in a bimolecular way to spit out fluorine gas and one equivalent of manganese trifluoride. Pretty cool reaction, but it's just crazy to me that we had to wait till 1986 to make it. Now, fluorine has lots of industrial uses. We use it in the production of metals like aluminum and steel. It's a critical component in Teflon. Okay, that's what gives Teflon its slippery properties. And so the other thing is this species right here. Anybody know why you should care about that? It's a chlorofluorocarbon, and in particular, this was the real baddie that was depleting the ozone layer. Okay, CFC 22. The reason it's named 22 is DuPont came up with this crazy naming scheme where the 2 in the 1's position corresponded to the number of fluorines in the CFC. The 2 in the 10's position was the number of, I think, chlorines plus 1. And then the fact that there's nothing in the 100's position tells you that there's only 1 carbon atom. So the number in the 100's position is the carbon atoms minus 1. It's just crazy, crazy numbering scheme. But this one is particularly reactive, and you can see that from this reaction even. If you heat it up to 600 degrees Celsius, I mean, that's a pretty unusual reaction, right? To take a methane analog, heat it up, and spit out the carbene. Okay? You actually eliminate HCl, you make the CF2 carbene, which then dimerizes to make tetrafluoroethylene. Turns out at DuPont, they accidentally discovered Teflon by having a cylinder of tetrafluoroethylene around that spontaneously polymerized, and they ended up with this mass of very slippery, unreactive plastic that now coats all of our pots and pans and this and that and the other thing. So fluoride is used in water fluoridation. Of course, we all know it's in our toothpaste as well. Interhalogens. So we always think about F2, Cl2, bromine, so on and so forth. You can get interhalogen bonds. Okay, so you can make the diatomics like, you know, the chlorine-fluorine bond, the iodine-chlorine bond, the iodine-bromine bond. Those are all good. They follow the ordering X, Y to the N, where X is the heavier halogen, Y is the lighter halogen, and then N can be, well, technically 1, 3, 5, or 7. Okay, so always the lighter halogen is the one that has the greater number. Y, electronegativity, and oxidizing power. So if we take chlorine and bond it with fluorine, we can make chlorine in the +1 oxidation state. We can take chlorine, make it in the +3 oxidation state by adding 3 fluorides to it. Or we can make chlorine pentafluoride +5 oxidation state. Can I drive home the point again that fluorine is a powerful oxidizing agent? Okay. It's taking chlorine, the 3rd most electronegative element on the periodic table, and taking it up to the +5 oxidation state. That's as far as you can go with chlorine, but if you switch to iodine, you can then oxidize it all the way up to the +7 oxidation state. You get this trigonal pentagonal this pentagonal bipyramidal structure. So you have 5 fluorines in the equatorial plane and 2 axial. Anybody want to hazard a guess as to what the point group is? Oh, forgot about that, huh? D5H. Yeah, right, because you have a mirror plane that's defined by the equatorial plane. You got half of those 20% points back. Okay, as you might suspect, even though fluorine can oxidize these halogens and reach these ridiculously high oxidation states for the halogen atoms, they're all still very reactive, and they tend to be fluorine transfer reagents. And so in some cases, you can even use these interhalogens to oxidize metal oxo complexes and give off oxygen. So cobalt oxide reacts with the chlorine trifluoride gas. You'll end up with cobalt fluoride as the cobalt-containing byproduct. You evolve 3 equivalents of chlorine gas and 4 equivalents of oxygen gas. This is some pretty nasty reaction conditions. And if you think about the fact that chlorine, right, is typically used as a reagent itself to oxidize and destroy other, basically in sanitation applications, the fact that you're producing it really is it's a pretty spectacular reaction. As if that wasn't enough, you can even make cations of the halogens. This is another one that just, it's like, you know, you do chemistry all your life and you think you have a good feeling for what can be done. But the fact that you can make chlorine difluoride cation, I mean, that to me is about as exotic as a cation can possibly look, right? We're taking elements that typically like to be negative, anions, and we're turning them into cations by combining multiple. It's crazy. There are also oxo-anions of the halogens, well, all of them except fluorine. Okay, as I mentioned, oxygen is the second most electronegative element on the periodic table, and so it can oxidize various halogens, and it forms an important class of anions. So there's a whole host of oxo-anion acids. So here we have the acid of hypochlorite, chlorite, chlorate, and perchlorate. And you can see that as we add more oxygens to the chlorine, the acid becomes stronger and stronger and stronger. Okay? Again, this should make sense to you because as we add more acids, the chlorine oxidation state is going up, and the ability of the molecule or of the anion to hold on to that proton is going down. So all of these are very strong oxidants, but they have different kinetic stabilities. So the most oxidizing thermodynamically is probably perchlorate. Okay, it's chlorine in the +7 oxidation state. It's got 4 oxygens. Yes, it's got 1 minus charge, but that's still chlorine +7. Thermodynamically, we go down perchlorate to chlorate to chlorite to hypochlorite. And then you have chlorine, but the kinetics of the oxidation, so in other words, the speed at which or the ease with which they start their oxidation reaction is inverse. So chlorine is kinetically the fastest oxidant, hypochlorite the second fastest. Anybody know what hypochlorite is? Bleach. So when you put bleach in the laundry, what you're actually doing is you're putting an oxidant in there that oxidizes up any organic compounds that are causing stains. And when they get oxidized, it destroys them and they become colorless. So you're doing oxidation reduction chemistry by adding bleach to your laundry. For those of you that do undergraduate research, you may do electrochemistry, you may prepare salts. If you haven't been told this, be exceptionally careful if you're using perchlorate counteranions, okay? Because again, they're very, very powerful oxidants, but kinetically stabilized. So they'll sit there and sit there and sit there and be happy, and then if you're not careful, if you do something wrong, like grind it with a metal spatula, you'll catalyze the oxidation reaction and they explode, okay? So people have lost fingers to perchlorate anions. So you have to be real careful. Now, as for this kinetic stability, again, it probably makes sense if you look at the structure. So with the perchlorate or the perbromate or the periodate, we basically have a tetrahedral structure. Looks the same in all 3 dimensions. You get resonance structures where you can move the double bonds around, and you basically stabilize it through this idea of resonance. You'll notice from this table that there are some oxo-anions that are missing. For instance, the BrO2, so that's bromite, is missing, and that's because in aqueous solution it disproportionates to the bromate and the hypobromic acid plus a proton. Okay, last of our P block march, the noble gases. Boring, don't do anything. They may be the only set of elements that's more boring than carbon, right? We all know they're perfect spheres. They exist in their elemental forms as the pure, as single atoms with really low boiling points. But it turns out, again, as many of you probably know, they can be oxidized. So if you take xenon with, oh surprise, the most oxidizing element on the periodic table, you can break up that noble gas configuration. And so xenon with 1 atmosphere of fluorine at 400 degrees C gives you xenon difluoride. Great fluorinating agent. If you need to, it's a very volatile solid, but if you need to deliver an equivalent of fluorine, it sure beats trying to pull out your gas burette and measure out this really toxic gas. You can oxidize the xenon up if you heat it, add extra pressure of fluorine and heat it to 600 degrees C, you can get the xenon tetrafluoride. And if you go up to 60 atmospheres of fluorine gas, you can get xenon hexafluoride. Okay, so this is now a noble gas in the +6 oxidation state. I wouldn't want to put a vial of it in my back pocket. These fluoride complexes of xenon will do other chemistry. So if you take xenon hexafluoride, put it in water, you can basically hydrate off the HF and make xenon trioxide. There's one for you. Why does that reaction matter? Xenon hexafluoride plus 3 silicon dioxide. What's the lesson there? Don't put it in your glassware, right? So literally what this is doing is it's etching glass. It's pulling silicon dioxide molecules off of the surface of the glass and making silicon tetrafluoride, okay? Have I mentioned that these sorts of fluoride complexes are very, very oxidizing, very reactive? Yeah, they are. Okay, xenon trioxide is explosive, so don't go make it in the lab and isolate it. But the others are more stable. Xenon trioxide is kind of special that way. And for all of these VSEPR rocks, it always gets the right geometry for these noble gas fluorides and oxides. The end of the P block elements. Now, you know, trust me, I know that when we're going through that stuff, it's hard to sit there and listen, right? And I know it's even harder to read the chapter and to figure out what you need to know for the exam. But at the same time, that kind of descriptive chemistry, that's where you get a real appreciation for where chemistry is used in the real world, right? What we use different, you know, what are the main uses of different elements, different kinds of compounds. These are the kinds of things that you need to know so you can go out and amaze your friends, right? Be like, oh, well, that's used, I know what that's used for. That's how we prepare aluminum, blah, 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 blah. And then everybody goes, ooh, you're so smart. You're a chemist. Okay. Okay, so Coordination Chemistry 1. They ran out of creative names, so we're going to go through chapters 9, 10, 11, and maybe 12, which are Coordination Chemistry 1, Coordination Chemistry 2, 3, and 4. But we're going to start with structures and isomers. So what do we mean by coordination chemistry, and why do we call them coordination compounds? And so it all goes back to acid-base chemistry. Transition metals are almost universally considered to be Lewis acids, And the ligands that we coordinate to them are Lewis bases. And so we have a Lewis acid, Lewis base interaction. The ligands are the Lewis bases that are donating at least one pair of electrons to the transition metal. Yay. This brings up the idea of a coordinate covalent bond. You will also hear this referred to as a dative bond. Okay, it's a very specific type of Lewis acid, Lewis base interaction. And I'll highlight this. It's a coordinate covalent bond is highlighting that you're using a neutral ligand or you're coordinating a neutral Lewis base to the Lewis acidic transition metal. Okay? So a neutral ligand or a neutral base is one that doesn't have a charge when the octet is complete. And so the reason that this idea of a coordinate covalent bond comes up is because you'll see something like ammonia. It's a great ligand for transition metals, right? We know that ammonia is a good Lewis base. And so it stands to reason if metals are Lewis acids, it should be a good ligand for a transition metal. And so you'll see this written in two different ways. This is probably the most common, where you just have the normal kind of single line connecting the nitrogen to the metal center. Okay? In Lewis structures, we know that that single line means that the two elements are sharing a bond and they have a sigma bond. Okay? And that's fine. You'll also see it written, and this is really a more complete way to describe a coordinate covalent or a dative type bond, because it's emphasizing the fact that ammonia is a neutral Lewis acid. So basically what this comes down to is that arrowhead is a way to count electrons. It's keeping track of kind of who those electrons belong to if everything is going to be neutral. Now, where you have to be careful is we also have anionic Lewis bases, right? Chloride. Chloride is a Lewis base, but it's got a charge. It's also okay to write chloride with a single bond. Metal chloride interactions, they're sharing a pair of electrons. Do not ever do this. Okay? I will hunt you down and throw dog poop on your front door or something. In, the flaming paper bag, it would be great. Do not do that. Okay? Yuck. Makes me very angry. We on the same page? But this can be a very useful way of drawing bonds between neutral Lewis bases and Lewis acidic transition metals. Okay, so a neutral coordination compound includes the transition metal and all of the Lewis bases that are coordinated to it. Okay, so here we have two examples. The triamine chromium trichloride, diamine platinum dichloride. Anybody know what's so important about the molecule on the right? Wrong. Catalyst for organic reactions. That wouldn't be interesting at all. I'll give you its super secret name, or I should say common name, cisplatin. How does anybody know? I heard it come from over there. Yeah, it's one of the most effective cancer drugs on the market. That's the drug that saved Lance Armstrong's life, for better or worse, depending on if you're a cycling fan. Okay, it's the absolute best drug for treating testicular cancer and several others. Okay. we'll talk a lot about cisplatin because it's a really good example for a lot of different coordination isomers and stuff like that. So the number of bonds in a coordination complex is not directly correlated to the oxidation state, the formal oxidation state of the metal. And so we can see that based on even those examples above. So in this chromium complex, the formal oxidation state of the chromium is +3. Okay. In the case of the platinum compound, it's platinum 2. And so you might say, oh, well, obviously the correlation is that the oxidation state is half of the number of ligands coordinated. That doesn't really work. But we'll talk a lot about oxidation states because it's one of inorganic chemists' favorite things to do is assign oxidation states to the transition metal in a coordination complex. Coordination complexes can also be charged. You can have complexes that are cationic, or you can have complexes that are anionic. So here, the example on the left, you can see what we've done is we've taken away one chloride and replaced it with a neutral ammonia. Now the complex is cationic. So in this species, this complex, the cobalt oxidation state is still or in this case it's +3, even though it's still a 6-coordinate complex. The complex on the right, it's iron with 4 hydroxides. It's a monoanion. The oxidation state of that iron center is also +3. So again, no correlation between the number of Lewis bases coordinated to a metal and the oxidation state. When we're talking about these sort of complex ions, the ligands that are directly bonded to the transition metal make up what we call the primary coordination sphere. That primary coordination sphere, the one that defines the geometry around the metal center, is what controls its electronics and, in general, its reactivity. The counter-anion or counter-cation typically has much smaller effect on the overall reactivity or properties of the complex. And so, again, there will be other, obviously, if you have a cation like this, you better have an anion around to balance it because we can't put charged species in a bottle. And they will make up part of what we call the secondary coordination sphere. Okay, so we know from Chem 51 that molecules can be really complicated, really complex. And as such, naming of these molecules can be a real pain in the keister, okay? It turns out to be true for transition metal complexes. So we've already been introduced to the diammonia platinum dichloride complex. But the truth of the matter is, it can mean several things. If you're just given that formula, well, it could mean cisplatin, the cancer drug. It could also mean transplatin. This platinum complex is square planar, so there are 2 different isomers. One with the chlorides cis to each other, related by 90 degrees, the other with them related by 180 degrees. Transplatin, not a cancer drug. Just gives you heavy metal poisoning. Well, now that's weird. You can have the triamine platinum chloride cation with the amine platinum trichloride anion. Has really the same, right? If you write out the formula, it ends up being PtCl2 ammonia 2. Well, now we're just being downright mean, right? We could put all 4 ammonias on one platinum and 4 chlorides on the other. The platinum with 4 ammonias is +2. It's a dication. The platinum with 4 chlorides is a dianion. So we have to have ways to name each one of these different isomers and identify them so that when I give you the name of a platinum compound containing 2 chlorides and 2 ammonias, you know what I'm talking about. All right. So we'll start by writing formula. When you write the formula of a transition metal compound, the metal comes first because it's the most important. We typically go with the ligands in alphabetical order by the ligand name, not by the formula of the ligand. And so if the complex is simple, brackets are not needed. For example, this tetrakis dimethylamide titanium complex. Well, that should confuse you because you'll notice that when I gave you the name, I gave you the ligands first, followed by the metal. But in the formula, we give titanium first, and then we just use parentheses to denote the correctly dimethyl azonido or azido ligand with the 4, the N. You can also include the oxidation state of the metal in the molecular formula. Again, this tells you something about the electronic properties and potential reactivity of the complex, and we'll talk a lot more about this as we go forward. If the complex needs a prefix or is ionic, we use square brackets. So here's our cancer drug, cisplatin. So just like with an organic compound, you have to give the regiochemistry. You have to give that cis in order to tell everybody that the chlorides are related to each other by 90 degrees and the ammonia ligands are related to each other by 90 degrees. You only need one cis because a schooled inorganic chemist will know that this compound has to be square planar. And if the chlorides are cis to one another, then by definition, the only 2 spots left to the ammonia ligands are cis to one another. So you don't need cis, cis, platinum, diammonia, dichloride. You just need the one cis. Same thing. Oh, so another example now for a dication. The platinum with 4 ammonias would go in square brackets with either the 2+ if you're just talking about the cation, or you could have the counter anions listed after it also in square brackets to denote the total formulation of the salt. So here's an example. The dipotassium tetrachloroplatinate. The cations come first. So 2 potassium. The potassiums can be in brackets. They don't have to be in brackets, so often they're left out. The tetrachloroplatinate goes in brackets because it's an anion and it comes second. If we include the oxidation state, it goes inside the brackets as a superscript following the platinum element. We never give the oxidation state for the ligands, okay? There are some exceptions, but we won't get to those in this class because, frankly, the ligands are just there to support the metal, which is the cool part. And here's an example where we have both the cation and the anion fully spelled out. Both of them are the charged platinum complexes. You'll notice within each set of square brackets, the platinum comes first, followed by the ammonia ligand because ammonia starts with A and it's the first letter in the alphabet. And then last is the chloride because C comes after A, and we do things alphabetically for the formulas. Again, for this combination of the platinum dication and the monocation and monoanion, both platinum centers are in the +2 oxidation state, but we would indicate them individually if we chose to include the oxidation state in the formula. Not required, but often helps you or the reader or whoever keep track of what the oxidation state is. Okay, so it turns out formulas are pretty easy. The names are a little bit more complicated. So first rule, when you write the name of a coordination complex, the name of the cation always comes before the name of the anion. Okay? We never talk about chloride sodium. Right? I mean, you guys know this, right? It's kind of a silly rule. Cation always comes first. The ligands are listed alphabetically by name, not prefix. So if you have an ammonia ligand, it goes by A. If you have 4 ammonia ligands, it doesn't go by tetra, it goes by A. The number of simple ligands is given by a simple prefix. For complex ligands, the complex prefix is used. This is where you should just roll your eyes and go, are you kidding me? Okay, why in the world would you have simple prefixes and complex prefixes? I mean, it wouldn't be too confusing to have 3 triethylamines bound to a metal, right? If we use the simple prefix, it would be triethylamine, like, you know, try harder or something. So no, that would be a tris triethylamine. So that's literally why we have simple prefixes and complex prefixes, because it just starts to sound ridiculous if, you know, you have 3 tries in a row. Number 4, anionic ligands get an O suffix. So every time you hear me say chloride up here, you should scoff at me and say, you're wrong. It's not a chloride ligand, it's a chloro ligand because it's an anionic ligand and it gets an O suffix. Neutral ligands keep their normal names except for a few isolated examples where we have to trick you and have special names. So it's not a water ligand, it's an aqua ligand. It's not an ammonia ligand, it's an amine ligand. There are 2 ways to deal with charge when you name a complex. The first is in the Stokes system. And in that case, you give the formal oxidation state of the metal, and it's given by a Roman numeral in parentheses after the name of the complex, or specifically the metal. This is commonly used, but it can be problematic. We'll see some of the problems that come up. The other is the Ewing-Bassett system. In the Ewing-Bassett system, you give the charge of the complex. Okay, it's given by a regular number in parentheses after the metal name. It's less common, but it's always correct. Okay. We will see examples, so we're going to go through a whole ton of examples on the next couple of slides. So metals and complex cations keep their normal name. Metals and complex anions get an 8, so platinate, for example, except for the oddball metals that you always wondered why they have that symbol on the periodic table. So if you have an anion for iron, it's ferrate. If you have an anion of a silver complex, it's arginate. Plumbate, because, you know, that's what plumbers do. Stannate, orate, so on and so forth. Okay, prefixes are used to designate the geometric arrangement of ligands when needed. We've seen cis and trans already. Cis and trans come up in square planar geometries. They come up in octahedral geometries. They can come up in trigonal bipyramidal geometries. You never have to worry about cis and trans if you have a tetrahedron, okay, because all of the angles are equal. A special one for octahedral complexes is FAC and MER. FAC for facial, MER for meridional. Okay, in the facial arrangement, you have 3 ligands on a single trigonal face of the octahedron. For the MER arrangement, instead you have 3 ligands on the meridian. I think of it as being a belt around the metal complex. Ligands that bridge 2 or more metals get a prefix mu with a superscript n. N is the number of metals bridged. We saw that for sulfur. Thanks for the reminder. I have office hours in 15 minutes. And then we have, many ligands have commonly used names that differ from IUPAC name, leading to even more confusion. So we've all seen this for organic chemistry. It's worse for inorganic chemistry. And just like organic chemists who refuse to use IUPAC names and they use the trivial or common names, inorganic chemists do the same thing. I can almost promise you, outside of this classroom, I will never talk to you about a metal oxido complex, which would be the appropriate name for a metal complex with an O2 minus, a metal oxygen double bond. I guarantee I will always refer to it as a metal oxo. Okay? Inside of this classroom, it's 50-50. We'll see. PR3 will exclusively be referred to as phosphenes, but they're phosphanes. NR2 minus, inorganic chemists always refer to these as amido-ligands. Okay? And then they'll get lazy and they'll talk about amides. And every organic chemist goes, where's the carbonyl oxygen? Right? Because that's what an amide is. And so this is where you see how you name things becomes important, and so we should really be calling that an azonido. And so there's a whole list in your book of the proper IUPAC name for a bunch of different functional groups or ligands in transition metals. And we do need to make a real effort to be consistent. Okay, we'll very quickly go through a couple of examples before we break for the day. So we've seen this. We know how to write the formula. The titanium comes first. Then we put the dimethyl azonido ligand in parentheses with the subscript 4. But when we come to name it, we flip and the ligand comes first. So tetrakis, dimethyl azonido, titanium. So the first example that I've given, I have a regular, I guess it's a Latin digit in parentheses with a space after the name. So that's the Ewing-Bassett formalism to indicate charge, and it's telling you that the charge on the metal complex is 0. Okay? It's absolutely correct. The second one that I've put up there, tetrakis, dimethyl azonido, titanium, no space, parentheses, Roman numeral 4. This is the stock system for charge. Now it's 4 because the stock system gives you the oxidation state of the transition metal. Sometimes that can be problematic. Now, how do you reconcile the Ewing-Bassett system saying that the charge on the complex is 0 with the stock system saying that the oxidation state is 4? Well, they're in a way referring to different things, okay? We know to assign the oxidation state to this metal, or to the titanium center in this complex, we take each pair of electrons that make a metal ligand sigma bond and assign them to the more electronegative element. Nitrogen is more electronegative than titanium. So the electrons in that sigma bond get assigned to the dimethyl azonido ligand. So each one of those ligands is a -1 ligand. That means we've basically taken all of titanium's electrons from it, and so it has an oxidation state of +4. A titanium with a +4 charge and 4 monoanionic ligands has an overall complex on the charge on the complex of 0. Okay? So one is giving us the oxidation state of just the metal ion. The other one is giving us the overall charge on the entire complex. We'll see lots of examples. We'll go through them next time in class. I will point out, if you talk to your TAs, if you talk to a grad student, They're almost always going to call the complex tetrakis dimethyl titanium. Feel free to tell them they're wrong and they need to use the azonido ligand name. I'll see you on Friday.